So we're here for the PhD dissertation defense of Usha Lokala. Three of the members of the examining committee, the advisor, Dr. Amit Sheth, Dr. Vignesh Narayanan, and I, who am formally chairing this committee for the examination, Marco Valtorta, are here again. And the other members of the committee, Dr. Amitava Das and Dr. Raminta Tanulaitila of Arizona State University, as well as Dr. Valerie Schelling, are connected remotely. So I believe we can start without further ado. Maybe Dr. Sheth wants to say a few words before we start, or can we just get...
No, I just want to thank all the committee members who have joined. Usha, start.
Hello, everyone. Good morning.
There is a comment online that they don't see the title slide, but they see slide 3. So they don't see the slide which we are seeing in the room. Yeah, looks like it's fine now. Thank you.
Hello, everyone. Good afternoon. Sorry, good morning. So today I'm here to defend my dissertation titled Knowledge and Ontology Enhanced Approach to Natural Language Understanding in Computational Social Media and Healthcare. My primary advisor and major advisor is Dr. Ramesh, and from Computer Science and Engineering Department, Artificial Intelligence Institute, UFSC. And my committee chair is here, Dr. Marco Valtorta, from CSC Department, USC. And my other committee members are Dr. Raminta from Arizona State University, Dr. Valerie from Wright State University, and Dr. Amitava Das from UFSC, and Dr. Vignesh Narayanan from UFSC. Thank you, everyone, for being here, and thanks to all the committee members for being here. So these are the building blocks of my dissertation. We'll start with motivation for knowledge and ontology enhanced NLU. And we'll look at the problems we solved and some key innovations and frameworks. We'll go with the applications. So for this defense, these are the main topics that we are covering, which is process knowledge and scenarios of process knowledge. And the problems we solve here are main concept analysis and mild cognitive impairment detection. And we go with drug abuse ontology and its applications, technical contributions, takeaways, and so a little bit about my PhD journey here. I started my bachelor's at Jawaharlal Technological University, Hyderabad in computer science. And later I did my master's at Northwest Missouri in computer science. My advisor was Dr. Dinai's Case. And later, when I joined Noisys lab at Wright State University, I got an opportunity to get a graduate study in big data and smart data sciences. I also worked with some technical tech giants in India in the area of supply chain management as a functional consultant at ITC Infotech, SAP itself, and Infosys Capgemini. So later, when I decided to do a PhD, I met with Dr. Sheth in 2017 spring. Later, in summer, I got an opportunity to work with him as GRA. I decided to do my PhD at Wright State, and later when we migrated to UFSC, I'm here in front of you. So it's quite a journey. So coming with the problems we solved. The ones highlighted in green are already appeared in proposal. And so from over 25 publications we have, 10 are included in the dissertation, 8 of which are already discussed in the dissertation proposal. And the first 2 are designated for this difference. So we're going to discuss process knowledge to predict cognitive impairment, and also the process knowledge guided language prompting to automate MCA. So those were the problems we'll be discussing today. The others we'll be discussing them briefly in comments.
So, if anybody from the committee has any issue, please let us know. But basically, there was just too much material to cover the entire dissertation. So I recommended that Usha presents, prioritize the material research she has done after the proposal, and she can review quickly if anybody wants to go back to the prior work that she has, so that that way we can finish it in less than an hour.
So these are the key innovations we made in the respective paper citations. And these are where the venues where we published some high impact journals and conferences here. So to introduce what is KOE-NLU and the motivation behind why KOE-NLU. So this approach it leverages both structured knowledge and ontologies to improve contextual understanding in AI systems, and with the applications in the area of information extraction, summarization, question answering systems, etc. So this approach provides enhanced context awareness, improved accuracy, and also better alignment with domain-specific knowledge. And we'll see some examples what we mean by this. So let us discuss the limitations of NLP and why we need this approach. So the current limitations are presence of long tail, contextualization, abstraction, personalization, and reasoning. And real impact is in the area of the areas discussed in this work are in the area of social media and clinical data. So what do I mean by learning the long tail? So, for example, this statement is talking about opioids, pain relievers, and opiates like fentanyl are being used for similar purposes illegally as consumers are addicted. So some statement. So the question we posed here to the system is, does fentanyl cause opioid overdose? So to understand that, to answer that question, the system needs to understand the long tail here. So first, it needs to understand firstly opioid or class of drugs, then about pain relievers, and then what causes overdoses. Without that kind of domain knowledge, the system cannot answer that question effectively. The other limitation is contextualization. So in applications like conversational AI or chatbot systems, it's important to understand, to have some common sense knowledge of the main entity of interest, and to understand its classes, subclasses from the things. Okay. Yeah. So it's important to understand the events of depression, subclasses, properties, and all, without which we cannot come to a conclusion. So this refers to contextualization, which combines both linguistic context and situational context. So next is abstraction, which is another limitation. So we define the task of abstraction as mapping a concept to a higher level concept. So humans often speak in a high level abstract concepts when explaining their decisions or ideas to others. So here we are using ConceptNet. For example, this sentence, how does benzodiazepine withdrawal happen by increasing stimulating chemicals? So we need to understand that benzodiazepine here is related to withdrawals. and thus heightened stimulating chemical production such as serotonin cause benzodiazepine withdrawal. So serotonin is a neurotransmitter here, and heightened stimulating that we refer have some difference from WordNet. So basically, the task of mapping low-level features to high-level features concepts here we call it as abstraction. Okay. So personalization, so identifying data point, specific information and integrating with external knowledge to construct a personalized knowledge graph. Here, what we call as personalization. For example, in here, a person's depressive disorder can be due to family issues or relationship issues or some clinical factors. And it also varies depending on gender, the symptoms described, especially for a disease condition. So all of these affect a context specific to an individual or a gender and consequently affect his or her symptoms and medications. So personalization is required in such cases. Then we have reasoning. So this text here is more of substance use related than mental health related. But when we ask the model why it predicted depression, there is no explanation as it is not inferring to any domain knowledge source here. So those are the limitations of current NLP systems, and this is why we need KOE-NLU. So we have so language models can better understand the context of user queries and provide more accurate and relevant responses. And this is where KOE-NLU steps in. Okay, let us discuss what is process knowledge. It is a step-by-step procedural understanding of tasks, and it requires domain expertise and workflow details. And why the process knowledge matters? Because it ensures context-aware and logically consistent outputs, and there is some coherence between the outputs it produces, and there is a better chance of interpretability of results when we have the output, and we can minimize hallucination and confusion in the large language model responses. How do we define process knowledge in healthcare? For example, to detect depression or anxiety or any other mental health condition or a disease condition, it follows the clinician or a medical professional follows a sequence of steps to diagnose it. So we define it as layers of clinical process knowledge structures on language model outputs, and it enables clinician guided models of underlying language model predictions. So this is why do we need process knowledge guided models for better interpretability, error reduction, and context relevance decision support. Okay, let us see an example on why process knowledge matters in prompting. So this example is taken from PET dataset. So this is a multi-turn dialogue system where user is interacting with artificial agent here. So here AI agent acts as the domain expert. Okay. So here what's happening is, with this example, as user is interacting with the AI agent, the knowledge graph is being constructed automatically, depending on the questions posed to the user. So user poses specific questions to extract the conceptual elements, and that guides the construction of knowledge graph incrementally. So for example, in the green squares, the first task, user will ask for the list of activities, and that guides the construction of corresponding KG. And the green squares here are activity nodes, and the yellow squares add some activities to the actor nodes. And those connections, in the last step, the user asks for the set of temporal relations between the activities, and the users that answer to add some relations that two arrows to the knowledge graph. So here some insurance settlement is going on, and it starts with the activities, who is responsible until the settlement is reached. Okay. So process knowledge here is knowing who, what, when, and how of the workflow. So this plays a critical role in prompting because it gives both the user and AI model a clear context and structure to work within. And instead of simply asking open-ended questions, we are guiding AI with knowledge of relevant activities and responsible actors here and the logical sequence. So these are the different approaches to integrate process knowledge. Some of the approaches that we are already aware of are neurosymbolic integration and domain-specific large language model fine-tuning. And we have human in the loop feedback, where we work with the human annotators to decide upon the output, if it is correct or not. And then we have knowledge infusion across sources. So here, that's about the process knowledge introduction and motivation behind it. So the problem we solved here is the main concept analysis. So we'll now see what is main concept analysis and why we decided to automate it, and what is process knowledge in main concept analysis, and the novelty and technical contributions of this work. So this is a discourse data example that was proposed in the dissertation proposal. So this talks about cat rescue picture description and cookie theft picture description. So this is a discourse task used in aphasia therapy to assess language skills. And in this task, a patient is shown a picture and asked to tell a story about what's happening in the picture. So the patient is asked to include beginning, middle, and end of the story. And patient can look at the pictures while telling the story. And we capture that audio output of the patient and transcribe it to a textual form, discourse text form, and we work with it to identify the main concepts. So these are two picture-based speech tasks, and the right side, we see a MOCA, which is a Montreal Cognitive Assessment Test. So this is a popular test to detect cognitive impairment, and this test is for testing four important components, which is memory, executive functioning, attention, language, and orientation. So this is currently done manually, and this is also one of the features that we use to predict the cognitive impairment. Okay, what is main concept analysis? So we know that we saw some discourse task, and main concept analysis is another assessment just like MOCA, which measures the informativeness of a discourse sample. And it focuses on some essential information, the story of a picture, identifying key elements like main verbs and some critical details. So this is how a main concept is evaluated from the transcript. And these are the labels that we generate, like accurate, complete, inaccurate, complete, ACIC, AI, accurate, incomplete, and II is inaccurate, incomplete. So it depends on, it starts from the absent. If main concept is not at all produced, then it is coded as absent. If some elements are produced, then we check for accuracy and completeness. And if one or more essential elements are not at all produced, then we give a different codes. So we have four different codes. So this is the approach contribution to this work. So the AI challenge here is LLMs, large language models. They struggle with clinical discourse text, and there is a lack of process knowledge integration in the large language model. And we struggle with low main concept analysis precision or recall. And this is where the novelty comes in. So we use fine-tuned transformer models and contrastive learning to deal with the first challenge, which improves domain adaptation. And we also have hierarchical multitask learning. So the main innovation here is we are able to calculate a knowledge augmented task specific loss, which we call as a dynamic loss function that integrates both structured process knowledge into the training of HMTL. So in HMTL, we are dealing with multiple tasks. So we deal with just the accuracy and completeness in the first layer, and we deal with main concept extraction in the second layer. So this is how our approach compares with the existing approaches. The first one is the existing approaches are integration of structured process knowledge, and we have enhanced prompt engineering techniques. And the other existing approaches. Okay. So this is how MCA coding is done manually. For example, the little girl was riding her bicycle. That is one main concept for the cat rescue description task. And the cat was in the tree because the dog chased it. So for each main concept, the scores are given, and this is how it is done manually, which is very intensive, and it takes about 45 minutes for each participant. That's what we got from the annotators. So what do I mean by accuracy and completeness here? Accuracy is wording, grammatical form, articulation, and inaccurate words, inaccurate main concepts, and reinstating the essential information. For example, the user restates the same information multiple times. That is one measure of accuracy. And completeness is if the discourse test contains all the main concepts extracted or not. So these are the coding guidelines for accurate. What do I mean by accurate, complete, inaccurate, complete, and all? So the approach that we have used for MCA automation is graph-based prompt engineering, where we capture and organize domain-specific process knowledge, such as concepts, main concepts, and relations between them, and the scoring rules. So we give weightage to each main concept if it is mentioned or not for completeness purpose. And then we have prompt generation from the graph, where we create dynamic prompts by traversing the graph to retrieve the relevant nodes and edges. And we have constraint-based decoding. After the language model generates an output, we validate it against the graph rules and requirements. And then we have ontology-driven prompting, which is another approach where we map the high-level concepts to the classes in ontology. So those are the 4 approaches we tried. So unlike the conventional approaches, which rely on chain of thought alone, this pipeline explicitly encodes domain knowledge as a weighted graph, and it uses to constrain the large language model answers. So for example, here we use domain-specific knowledge graph, where we have graph encoding main concepts, relations between them, and the scoring and weightage rules for each concept. So each node in the knowledge graph will have a priority or a confidence weight. And during this concept extraction, we have high priority nodes are checked first so that we get the relevant main concepts. And we also have symbolic retuning with statistical feedback and human in the loop annotation. Once we have the output, this is evaluated by the subject matter expert, whether that concept is extracted correctly or not. So the contributions made to this work is domain knowledge graph, and we have multi-stage prompting and adaptive self-correction and feedback and reinforcement. So in the domain knowledge graph, we have nodes, main concepts, synonyms, and all for all the discourse text, main concepts and the relations between them, so that every main concept will get mapped to some class in the KG, some entity in the KG. And we have multi-stage prompting, where we have extraction prompt, validation prompt, and scoring prompt. So extraction prompt here focuses on capturing concepts with minimal domain expertise, and validation if each concept aligns with the synonyms or required attributes or not. And then we have a scoring prompt, which checks for completeness of the and accuracy. So that is how we have a multi-stage prompting in here. And we have adaptive self-correction, which is a novel thing here, where we have a violation detector. It's an algorithm comparing LLM's output to the domain knowledge graph constraint. And here we work with a short correction prompt. We correct the prompt if we get the wrong output, so that the model adapts to self-correct the prompt itself. And then we have feedback and reinforcement. These are clinicians and domain experts will see the final annotated transcript and accept it or not, correct or wrong. But this will also scale up this feedback and reinforcement will also scale up the number of data points we have, so that we need not work with the minimal gold standard data. So this is the overview of PKG-LP framework, process knowledge guided language prompting framework, where we have clinical discourse text and ontology-based structured knowledge and graph neural network encoding, and hierarchical multitask learning, where task 1 is main concept identification, task 2 is we check for accuracy and completeness, and task 3 is discourse coherence analysis. Okay. So these are the okay. So this is the ablation study we have done. So we started with full more proposed approach, which is PKG-LP, and we took off no weighted graph between it, so which lacks concept prioritization and all, and there is no precise information identifying the main concept elements. Then we have say single stage prompt instead of multi-stage prompting, and no self-adaptive correction model and no human feedback. And the results varied depending upon the traits of the model. And let us see an example. So this is the performance of model on cat rescue task with baselines as GPT-3, zero-shot modeling and fine-tuned BERT, and graph-based large language model, and then PKG-LP. So here, this is the extracted main concepts here are for cat rescue. And why our approach is performing better in here is we are enforcing correct event ordering using structured process knowledge prompting. And we are linking concepts in a causal chain in our graph. So we have graph-based knowledge integration. And we are also balancing precision, recall, and coherence as we are doing a multitask learning in here, as we are learning step by step as task 1, 2, and 3. So these are the extracted main concepts for each model, and these are the observations made. So for example, in our PKG-LP approach, we have a kitten and a fire department called. So here we have some key actions and an event flow between those actions, which maintains coherence. Okay. So as an extension to this work, so we automated main concept analysis for discourse tasks. And we also want to look for analyzing and detecting cognitive impairment itself without MOCA test and just using the discourse text itself, if we're able to detect mild cognitive impairment or not. That is what we are trying to look at. Okay. So this is the motivation behind why we are using process knowledge to predict cognitive impairment. So as I said, discourse analysis is a sensitive measure to identify MCI. So it is a transcribed speech of several picture description tasks of a patient. And evidence shows that use of this kind of spoken language is a great measure to identify mild cognitive impairment. And we know some cognitive changes occur naturally as we age, and more research in this area will help us to find the subtle differences between language production in normal aging versus impaired adults or healthy controls. The existing models for diagnosing MCI, mild cognitive impairment, they require extensive and invasive neuropsychological evaluations or some specific tests like MOCA or MINI. There is other test called MMSC, which is Mini Mental State Examination. And there is another test where we automated main concept analysis. So those are the tests to decide upon if an individual has MCI or not. But we are trying to see if the discourse text itself with all its features will help us in automating the process. Of course, there are scalability and accessibility issues too. So let us see what features that we worked with for the discourse text. So for each discourse text, we have semantic, lexical, PNC, and sentiment features. And we also have speech features like audio, acoustic analysis, standard deviation, pitch, harmony, when the audio is being recording. We have all the audio features of the text. And we have demographic features like race, education, gender, and income status. So we worked with all textual, speech, and demographic features for the each discourse analysis text. Okay. So for example, this is the text extracted from cat rescue picture, and we automatically extract number of utterances, percentage noun, and verb index from the text, and proposition density. And we use MOCA score to label this text. So we have MOCA scores for all the discourse text here, and we use that to label the test initially as mild, moderate, or at risk. And we try to, we have the data is combination of both healthy controls, that means healthy adults and also impaired adults. So this is overall framework for MCI.
Can I ask a question on detail on the previous slide, please? This is a very small detail. I noticed in the dissertation it was the same thing. You in the cat rescue text, you have periods followed by lowercase letters. Is this standard in this kind of transcript? Because it's grammatically correct. You also had she had as she go her father. You would have expect the bird continued to tweet as she go her father. I would have expect continued to tweet as she went fetch her father or something like that. Again, what is going on here? It looks like these are not correct.
So that is a raw speech of
Okay.
patient. So that is how we got the audio converted to text as. But we don't alter the text, or we don't do any kind of data cleaning to just preserve the several traits of it, like utterances, number of caps, pauses, fillers, and all.
So there are no pauses. I know in other places you mentioned that adding pauses. I can't remember the exact name of those things, but something
Yeah.
like that. I don't see that.
Yeah, this
here.
is in this example, we don't see it, but we have it in our data set.
Okay.
Yeah.
Thank you.
A quick question. What is Barb index?
What is what, Dr. Das?
Barb index.
Is it Dr. Das?
Yes, yes.
Okay.
Verb index, verb index.
Yeah. What is Barb index?
Verb index is related to syntactical feature, and we have a formula for it, like number of verbs used, something to the total number of verbs present in that discourse text. I think I have a slide for it.
Okay. Okay.
This is a pronoun index, number of pronouns by total nouns. That's total pronouns. So verb index is number of verbs by total verbs found in that text. So, does that answer your question, Dr. Das?
Yeah. Fine. Please go on.
Okay. So coming to the pipeline. So this pipeline includes automatic discourse feature extraction and cross-cognitive domain attention mechanism here to predict cognitive decline from raw spoken discourse text. And these are the features that we work with, like textual features, audio features, demographics, and we have MoCA in place to label this data. And technical contribution here is we are trying to incorporate external knowledge from ConceptNet into the CCDA model to enrich the input data representation and to leverage common sense knowledge related to the entities of interest. For example, if you are trying to see if everything is mentioned in the discourse analysis or not, we are trying to map all the girl names and all the cat names and all to try to figure out. So because some patients will not mention the cat or little girl, instead of the cat, they will mention Sally or some cat name that they know of. So it's important to get some common sense knowledge of entities in here. And this is also introducing a new approach to compute cross-cognitive domain attention, just focusing attention heads specifically on relevant main concepts, which is cat, little girl, for example, in here. And we are not focused on, so we are just trying to imitate how it is being done manually. So when manual coders do this kind of task, they don't typically look for exact grammatical construction, articulation is accurate or not. Instead, they look for if all the main concepts are covered in the discourse text or not. So that's how we are trying to imitate how it is manually done without making it very fancy. So we have formulas in place here for pronoun index, proposition density. So all these are calculated from the discourse text itself. Okay, so the core of the attention model that we proposed here, CCDA, cross-cognitive domain attention, it is a scale dot protection product attention mechanism, which assigns selectively higher weights to the main concepts of interest. For example, here it assigns higher features to linguistic and speech features that are most indicative of cognitive impairment as per literature. And this mechanism also operates within our transformer-based architectures, enabling the model to focus on key components of a verbal response. And it also filters out the less relevant elements, and the attention is computed as this, where Q is the query, K is the key, and decay is the scaling factor to prevent.
And what is T?
is the transpose function here. And A represents the attention weight matrix. And this mechanism is enabling the model to recognize all the features that we mentioned, like lexical, syntactics, and discourse level indicators of cognitive decline. So these are some examples on how our model performed on cat rescue description task. And the MOCA is the label that we used. And these are the predictions made by the CCTA model. So to further zoom upon the transcribed utterance of a cat rescue here, this is another example of a real description. And the gold label assigned is MOCA 19, which is MCI, mild cognitive impairment. So it depends on the MOCA score, what label that we assign to the text. And excuse me. So the predicted label for the model is also MCI. And confidence score we have here is 0.82. So here the high weights given to the tokens, they signal narrative confusion and potential disorganization, like repeated mention of, for example, ladder, mention of loses his grip or very chaotic, those all. And external knowledge about atypical cat rescue narratives from ConceptNet helps our model to identify that losing grip, child crying, mother waving arms, and father being uncertain here in this text. And we have cross-domain attention that integrates acoustic and other signals and demographic data to further refine this classification. So
Since
with that,
since you are moving to another section, I have a couple of questions. So I'm just trying to understand. So main concept analysis, you are trying to find, as you said, you are trying to find out the main concepts, present in the language. And you are not doing anything fancy, you are just extracting all the concepts are present or not. So my naive question is how this is different than topic modeling, topic extraction from text. That's number one. Number two, you just presented a very soft, very naive softmax function. So to get cross attention, you have to probably retrain the network. So if there is a token is the unit in your text and you are trying to get cross attention to the speech, so what is your unit there? So is your utterance level is the unit? So how did you get out of only softmax the attention? So these are two questions, if you can quickly just address.
to answer your first question, so how it is different from topic modeling, the main concept abstraction. So we tried topic modeling and it didn't work out because discourse analysis is quite complicated. And as you can see with several examples, there is no clear mention of the main concept at all. And when we introduced multitask learning, in the first year, we learned only the main concept extraction, and we check for accuracy and completeness depending on the coding, depending on the actual coding we have for this MCA. So we follow that coding and we try to embed that process in the model so that it differs from just typical topic modeling thing. And for the second question, the cross-cognitive domain attention is calculated across speech and speech and textual features and also the demographic features and for that particular discourse text and not just the discourse text itself. So I think
You are getting
it's
this, you are getting that K and Q from language model or multimodal model. That your
can
softmax
you
equation. You have an equation, right? Q and K and then by DK. So you are getting those softmax from a language model or a VLM?
or from where?
VLM or multimodal model.
So we are getting it from multimodal view. So we are assigning higher weights to linguistic and speech features, which are most indicative of cognitive impairment. and that operates within the architecture. And so that comes from a multi-modeling of there are several features, and it's not just a single dot product attention mechanism. Does that answer your question?
Sure. Please go on.
Similar to what Dr. Has's first question, when you're doing automated MCA and you're creating the labels complete, accurate, incomplete, inaccurate, and those 4 labels, you're comparing against the manual MCA coding, right? And you have that for cat rescue and cookie theft discourses. What happens when you have an unseen discourse for which you don't have a manual MCA coding and you still want to automate that process? How do you check against it, and what is your ground truth to evaluate the labels?
So right now, the current clinical guideline is to use cat rescue and cookie picture descriptions only. But there is something called Cinderella. I don't remember. It starts with Cinderella, so the other picture description task. So if you plan to include another task to the model, you have to update the graph with relevant entities and all, and have at least few gold standard data for that to scale it up.
So for an unseen discourse, you would still need to have a manual ground truth coding of it.
Yes. Okay. So with that, I would like to introduce drug abuse ontology. This ontology, we have used it in several of our works, and it's good at improving the model performance and try to understand the entities of interest in the domain of addiction, and what the several slang terms and product names that we find in social media and stuff. And we'll discuss briefly about the construction of drug abuse ontology, and then we'll go about some applications of it, and we'll see how this is helpful. So this is designed in Protege, which is a popular ontology editor that we use to build the ontology as a tree of subclasses. So here we are showing classes of substances like cannabinoids and opioids. This is populated with subtypes of these substances like morphine or fentanyl, and each substance is defined by its name, and when applicable, information regarding its pharmaceutical name, brand name, slang name, street name, and all are updated in the ontology so that we capture such entities from social media data. Okay, so here what we see the instances here in purple, those are the instances of the classes. This is like creating instance of classes in a hierarchy, and the instance of class has its own class and it fills a value for that. So it has properties. For example, fentanyl belongs to a class opioid, and it has its own properties like has brand name, has synonym, has slang term, etc. And Dow here reuses instances from DBpedia dataset, for example, buprenorphine in here. So we have ontology-based annotations here. So this describes how texts are automatically annotating using Dow to identify drug entities, dosage, time interval, route of administration. If the text is given, we're able to capture all this information from in here. And in tasks like lexical, semantic, or syntactic analysis of textual data, adding this kind of ontology as external source, it will help us extract triples and entities to populate the graph and add some conceptualizations to the drug use domain. Okay, so these are the semantic web tools that we have used to evaluate Dow. So Dow ontology is evaluated for the following criteria, like its impact, reusability, design, and technical quality. So we have used several tools to evaluate ontology. So we call this method as perfect O, ontology improvement. So these are the checkup levels. So we start from syntactic validation to ontology consistency, and we use a different tool for each of these. So perfect flow ontology is a highly cited way to evaluate any ontology. And these are the results when we evaluated DAO for these tools, WebOwl, Vapor Checker, and the other tools that you see in here. And this is the final ontology metric. So these metrics list the numbers for structures and representation of ontology in Protege. And Protege is the most widely used tool to create ontology. And here axioms associate class and properties and a combination of logical and non-logical axioms. And the number of distinct classes, object properties, data properties are focused on how we are evaluating the structure of DAO. Okay, so let us look at the scenario 1. So this already appeared in the proposal and we would like to discuss it briefly. So we are trying to understand mental health symptoms using knowledge-infused multitask learning framework. So this framework is presented before, and here we develop a multitask framework for identifying mental health symptoms that consider gender language used in a health condition related post. And this is the first study in the domain of CBD that considers both gender language in a mental health related post. So to justify variations in gender related description of symptoms, we propose a gender enabled mental health framework, which we call it as GEM. And this performance of GEM is improved for the task of symptom identification along with gender identification in a multitask learning paradigm. And we compute attention over 2 encodings for generating a single mental health context aware representation of gender text. So this is a technical contribution, a GEM framework, and a bioencoder model that separately encodes symptom and gender text. And by integrating gender embeddings with word embeddings and applying the multi-head attention mechanism, the model becomes capable of focusing on both gender-specific language patterns, which enhances its symptom differentiating capability depending on gender, which is very prominent in CBD. And coming to the scenario 2, where we employed DAO to understand cannabis and synthetic cannabinoid use. Here, the problem we solved is the association of cannabis use with depression. And this is the text we have taken. So here we have entity locator module, which uses DAO to map input words in a tweet to their corresponding entities in the ontology. And the process involves computing the edit distance between the entity names from the DAO and anagrams in the tweet. So the identified entities are then masked to provide model with explicit entity locator. For example, all the entities related to cannabis in the post are masked as cannabis, and all the depression related entities are masked as depression. So we are going, we got if any of this term is mentioned in the text in the tweet, we normalize it to the single entity. I would like to go quickly in the interest of time. So we have gated K BERT framework here, which has 3 modules, which is entity locator module and entity position aware module and encoding module. So entity position aware module, as the name says, it infuses knowledge of entity positions into the model to better capture the contextual information. And it has several layers inside it, like position embedding layer, convolution layer, and attention layer. And we have encoding module to obtain a comprehensive representation of tweet by leveraging both the language model and CNN-based position aware module. And we have BERT representation. So the novelty here is a gated feature fusion, where we are combining the features from both the model and the position aware module to have an optimal way to join these features by applying a sigmoid activation function. So here we are trying to classify a tweet into one of the relationships of reason, effect, addiction, and ambiguous. So what we are not able to classify, we classify it as ambiguous.
Can I ask a quick question? So if
Yes,
you're
Dr.
using transformer-based model, then definitely it has a positional encoding. So why do you need a separate positional encoding to be learned? And why do you think CNN is the right way? Because CNN actually disturbs the positions. It only, learn the relative positioning.
This work is done in 2021. So at
But
that time,
still BERT, right? Still BERT.
yeah, yes. So we came up with the gated feature fusion because we are working with two entities of interest here, where is cannabis and depression. So how many times those entities are mentioned in here in the tweet? We are working with both of them, and to join these features, we have the contribution of each feature set to the final representation. That's the reason we have gated feature fusion. And yeah.
Sure.
So
I'll
what
not
is the
take more
question?
time. No, I will not take more time. My question is your basic language model here is BERT, right? And BERT
Yes.
uses transformer. A transformer typically use sine cos positional encoding, right? So positional encoding is there somewhere. So the motivation, but anyway, we can take it later. So please go on.
Okay. So the scenario 3 here is addiction, dealing with substance use of these drugs. And in this, we actually see which drugs are contributing to addiction, and if we are able to find some conclusion from the reflection of crypto markets on social media. So for this study, three crypto markets, Dream, Tochka, and Wall Street market are periodically crawled. And here we analyzed social media data from opioid users to understand what are the behaviors associated with opioid use and to identify what kind of feelings are expressed. And over 70,000 opioid related listings are crawled in dark web, and over raw HTML files are collected and they're parsed, and all this data came from, this is a sample data that came from the dark web, and this is social media data that we are able to extract using this product information, and these are the comparison of several drugs, sentiments, and emotions. So after doing such work, we are interested to detect substance use, whether the user is addicted or not, basically. And this is a knowledge and time-aware analysis we call. And initially, opioid-related listings are crawled from crypto markets and social media data. Accordingly, for those products found on social media are collected from the subreddits and Twitter using a lexicon derived from Dow. And we have bird-based models here used to generate sentiment and emotion labels for these social media posts. And then this framework integrates historical sentiment and emotion for that post with the current post encoding to predict whether a post indicates substance use or not. So this is an end-to-end system which enables detection of substance use disorder trends, and it can be helpful to inform public health interventions by analyzing reflection of dark web on social media discussions. And this work is also published as a media article, which I'll be showing later. And these are the takeaways from this presentation on how does knowledge help in health and epidemiology domain, and the data sources we referred and the knowledge sources we referred from, and how does this enable insights, emerging trends, and how to automate several clinical guidelines. And we're able to make some real impact in finding the emerging trends and the relationship between drug and mental health relationship, like cannabis and depression. And we are also able to automate some concepts like some tests like main concept analysis and the need to remove MOCA to detect mild cognitive impairment. And we also studied how the interesting topic of how the dark web products has some reflection on social media groups and substance use detection on social media. Okay, these are the publications we had regarding this work. This is a special slide for me, and I'm very thankful to the amazing faculties and industry leaders from diverse backgrounds here with whom I collaborated during all my PhD research and journey. And I learned a lot, especially from interdisciplinary collaborators here, Dr. Valerie Shalin and Dr. Raminta and uh, Dr. Mariam Panahizyar and Dr. Nitin Agarwal and Francois Lamy, to mention a few. And I also collaborated with subject matter experts like KOE-NLU people in here, where I learned a lot from them. And I'm especially grateful to my advisor, Dr. Sher, for guiding me through all this journey, for giving his critical reviews and making me strong day by day. So this resulted in some successful prestigious research grants at NSF and NIH or NIDA as a collaborative grants where I got an opportunity to work as a student investigator. So I also have worked with some students with uh, different backgrounds and nationality and all, but they're all great. And I learned how to collaborate with uh, several mentees in here, and this resulted in tutorials, invited talks, publications, and also some media articles. And students are now working at several places and in a good positions. And I'm fortunate to mentor like 7 students here coming from USA and other countries too. So this is the overview of my research methods we have employed and application areas and the funding agencies. I'm grateful to the funding agencies which have funded my work here, and collaborations with interdisciplinary team like SITA at Wright State University, and also Aging Brain cohort for the main concept analysis and MCI prediction work at Arnold School of Public Health. And yeah. This is the media article. Can AI address the drug abuse problem for the interest that is created on our substance use work and addiction work? And this is another media article around the same thing. So we disseminated our research through invited talks, tutorials, and all. So this is how these are the venues where we gave talks and tutorial set. These are the funded projects that I worked with. So they are coming from NIH, NSF, and NIDA. These are the open resources where we released our ontology and the other things, depression drug use and depression lexicon, where we solved association with cannabis and depression. That lexicon is also released for public use. Okay, this is the addiction and mental health work we have done at ASC. So here we have all the related mental health and addiction work that is mentioned in this dissertation today. To mention some few of them, we have EDAR Friends, which is an IDA funded project where all the addiction work came from. And we have e-drug trends, where all the cannabinoid use and drug abuse ontology work that came from, and PRIDOS, which is prescription drug abuse online surveillance, and epidemiology, which is also another project where this work covers. These are the research wiki pages for all the work covered today. So these are the references. Thank you everyone for listening to the dissertation today, and I'm open to your questions.
Okay, thank you, Ms. Lokala, for this presentation. You took a little more than an hour, which was very appropriate for this. So now we can have questions from everybody, audience and committee, and then we will close questions from the audience and just have questions from the committee for a while. So maybe I should ask if anybody who is not on the committee has questions now. Okay.
Question regarding your gender-enabled message.
Can people who are, yes. So let's move the microphone.
Right. Could you go back to that slide?
Which one?
The gender-enabled methodology. So, to the best of my knowledge, mental health issues in females have been severely understudied and under-researched for several decades now. So, when you were trying to model this, the lack of research on female mental health disorders, or the disparity between the studies that have been done on males versus females, was that an issue for you? Or if it was, how did you tackle it, or how did you mitigate that problem?
So when we are collecting the data itself for gender specific content, we got some information from the University of California at San Francisco Hospital that they need to mention. So we are studying this particular problem in the area of cardiovascular disease domain. So they have all these EHRs where patients needs to mention even the mental health symptoms. That's where we got the reference from, and we are initially collecting the data.
Right. So my question, however, was when you came up with this model, did you face a problem because there was lack of sufficient research on females with respect to mental health disorders, or was that not an issue for you?
It was not an issue because we are able to identify specific subreddit groups for only the females in this domain, so that it was quite an easy task for us to identify it.
Nice. Oh, thanks.
Good. Any more questions from the non-committee audience?
Hi, this
Maybe
is Michael
online?
Humes.
Okay, very good. Thank
Sorry.
Go ahead.
A knowledge graph, typically, the nodes in it are nouns. Things like cat, tree, father, girl. Process graphs are typically verbs. Climb, rescue, things like that. So in your development of process graphs, how do you take advantage of this, sort of the distinction between nouns and verbs? Just in general.
So when we capture the nouns and verbs in the discourse text, we have separate, we treat them as separate features in the model. And we have separate formulas to calculate, to count them in, like percentage noun index or percentage verb index and stuff. So we are seeing it as different aspects of this discourse analysis.
Okay, thank you.
Is that your
I don't see any questions either in the chat or or online from non-committee members anymore. So questions from committee members that are suitable for the general audience too. Let's start with that.
Yeah.
Okay. So Vignesh, do you want to give a good example? Let's start.
Sure. Just a general question. So you mentioned in the work where you had multimodal data integration, but you had little information on the slides about how you processed audio recordings or the speech recording. Right? So would you like to elaborate a little bit about what you did with that data?
So, regarding audio speech feature data extraction from the discourse text itself, we used a tool called AutoClan. So that tool will give us this vocal parameters like the speech harmony, shimmer, and standard deviation, and also we are able to extract features from that for that discourse text.
And how did you use it with the text?
We used it along with the other features too in the model.
So
So
you appended these features with the text features. Okay. Any other, did you try using it in any other way? Just
we tried using it in a different way, but due to the limitation of this data set, the other models did not perform well, like using speech itself as one modality and then using only the textual features as one modality and all, because the data we have is limited. We have about 400 samples of this data set. Yeah, because it is associated with MOCA, which is a cognitive assessment test itself again. So such kind of data is difficult to find, and we have limitations on that.
I think Valerie has a question.
Hi, Usha. Vedant had me convinced that there were existing apps that could detect gender and age. So what's the special issue that you are addressing in your work that is not covered by those sort of generic apps that tell us whether it's a female or a male and how old they are?
So which work we are referring to here, Dr. Shalin? Is it
The-
NCA?
The mental health symptoms, yeah, and the special language of females in there.
In there, so what we are dealing with is we are dealing with coexisting symptoms like mental health symptoms associated with CVD for a specific gender. So this is not something generic that a model can predict just the gender and age, but we are trying to understand how these symptoms are described in the text, and we are trying to predict the mental health symptom itself. We are not predicting the gender.
Yeah, but you could conceivably run one of Vedant's apps and subtract out the effect of gender to see what the unique piece is that you are contributing by understanding basically what it is the interaction of gender and mental health symptoms. That would be a good baseline to compare against.
That is true, but as we are working with gender identification along with symptom identification here, we treat it as a multitask learning area where we are not just trying to predict gender in here, but we are only dealing with a specific disease condition. But yes, that can be used as a baseline, Dr. Shalin.
I don't see any hands raised from the committee. online, and so maybe we should ask the audience to leave at this point. Okay, thank you. So thank you for attending, everybody in back. See you later.